Okay. Yeah, as I was saying, we're going to have just a couple more stats lectures, and then Saturday there's going to be a sort of intro to ML day. That's what I like to do prior to the last day of class, and then on Monday we're going to go over we're kind of together going to do a mock interview for the technical interview. We're going to take some probabilistic problem and break it down into various forms, pack things into dictionaries, do some analysis, and go from there. Today we're going to talk about continuous distributions. There's going to be a bit of just watching me code that happens today, and let me think about a good way to say this. You might see something from this on the technical interview, right? We're not going to ask you about the normal distribution. That's something, it's kind of a huge topic, and it's a topic that you should know, but you're going to encounter a lot of it when you learn the central limit theorem in the DSI or in the pre-course for the DSI. And you're also going to, when you get into inferential statistics in the pre-course to the DSI, you're going to cover the normal distribution quite a bit. As far as the exponential distribution, the takeaway from today is really going to be the exponential distribution model. You can use it to model time between Poisson events. So that's how we're going to think about it. The uniform distribution that I'm going to code through some things here to give kind of an underlying basis for a type of uniform distribution. You're probably going to see something like that on one of the technical interviews. So, let's just get started. I've revamped, as you probably realize, I've been rebuilding all these slide decks as we go. So if things are a little bit bumpy here and there, sorry about that. But and for some of you who are starting, who have gone through the premium prep before, there might be some new things that you see here, and that's going to be true for the next couple classes as well. Okay, so we've talked about discrete random variables. Today we're going to consider continuous random variables. So just to give a quick reminder of a way to think about the difference between discrete and continuous. Apologies, I know you've probably seen me do this a lot. So we have 0 to 9, and this is going to be discrete. How about that? And this is just 1 through 8, right? 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. When we're thinking about something as being discrete, I like to think of it as we've got clear bounds, right? So it's 0, 0, 0, 0, 0 until you get to 1, and then it's 1. There's nothing in between 0 and 1, right? So when we're thinking about something as being continuous, we're making a sort of assumption, and I'll say this is from 0 to 1 here. We're making some assumption about infinite precision. And if I take a point here, 0.4 or 0.3, let's say, this isn't just 0.3, this is 0.3, 0, 0, 0, 0, 0, 0, 0. At some point, right, there's going to be some decay in our exactitude, right, in our instrument or our ability to pinpoint a specific value, 0.3. Really, the value 0.3 is kind of this theoretical value, and in reality, if we have an infinitely precise instrument, it doesn't actually make sense because we don't have infinitely precise instruments. But if we had an infinitely precise instrument, then we could sit here and measure this out, and maybe there's a 1 and a 9 and a 7 out here somewhere. For our purposes, though, we tend to only need a certain level of precision. Even still, underlying the continuous distribution, if we're talking about an exact value, then we're going to think about this as having the potential to be infinitely precise, right? And this kind of leads back to the idea of, we pinpoint a value on this, some value between 0 and 1, if we pick a specific value, right, and maybe it's this point, this hash mark on this line between 0 and 1, if we want to consider the probability of that specific value, if we call it, n, the probability of n here. Well, the probability of this is, if we're considering infinite precision, again, is going to be 1 over infinity, which is going to be 0, right? So keep that in mind, that when we're thinking about something, something from a continuous distribution, we're not just thinking of a specific value. We're thinking of a range of values. So in this case, maybe we're talking 0.3 to 0.30000000001 or something like that. And then we could, take that, that range of values and think of that in a discretized way, right? And that's really how we want to think about continuous distributions. And we'll get into that when we get into probability density functions in just a minute. So for continuous random variables, we use a probability density function as opposed to a probability mass function. The only real difference here is, the PMF gives us a probability for a discrete outcome, right? Like when we're thinking about Poisson, what is the probability of, 9 things happening in 5 minutes, given that we expect 20 things to happen in 5 minutes, right? That's a discrete thing that we're looking at. We're saying, okay, well, what's the probability of 9? 9 events occurring. Whereas the PDF gives us a probability over an interval. And that's kind of what I was getting at before. We need to give it a range to provide us a value. And we're going to think about this in a couple different ways. The main way that I'm going to present it is we're going to discretize aspects of a continuous distribution. So, fundamentally in a computer, even if we have all values from 0 to 1, in some deep way, no matter how we encode that, it's not truly continuous, right? We've got this idea of a 64-bit float, and a 64-bit float is going to have, some discrete number of different, some discrete bounds on the number of values that it can represent. As far as a 64-bit float goes, I'm not sure what that is offhand, how many different floats you can represent, but it is a limited number, right? And so we never really have something purely continuous with a computer. We have something that is pseudo-continuous, and when we're thinking about that, that's, floats, 64-bit floats. Again, as I said, in a continuous distribution, the probability of a single exact outcome is going to be 0, because anything divided by, anything that isn't infinity divided by infinity is 0, right? So here's, let me maybe keep that a little larger. So we're going to, visually, when we think about the probability of a continuous outcome, we're going to maybe represent it as the area under the curve of some function. So I'll just snag this little bit right here, right? This is our classic, the probability of outcome A is the cardinality of A over the cardinality of S. Well, in some sense, we're going to divert away from that, because this is sort of speaking in terms of the count of the elements, right? So let's think about this in terms of maybe just a polynomial, right? We have some polynomial function, and I'll keep this fairly simple. I'm not going to define the polynomial necessarily. I'm just going to plot it. So Why don't we do that? So let's say it goes like that, okay? Now, if we're trying to discover the probability of getting a value between this and this, then we might, instead of thinking about the cardinality, let's say that this section, we name it A, right? This section is A, and this whole section is S. At this point, we're not really thinking about the cardinality, right? Because we're not necessarily counting the instances of A. We're thinking about this in terms of an area. So this is not exactly relevant anymore. But it's a similar idea, right? We can still take A and divide it by S, and that's going to be the probability of A, right? If we're talking about A as being this region and S as being the entire region, right? The entire region. Okay, so when we get into this, there are a couple ways to do this, and one way is through integration. We're not going to be doing any calculus here. Well, let me say it like this: we're not going to be doing integration in the way that you would learn it in, say, a Calc 1 class. We're going to be approaching this using the concept of a Riemann sum, and I'm going to try to just make that really simple. It sounds complex. If you haven't seen Riemann sums before, the idea is actually really simple. So I'm going to draw this polynomial again, and I don't know, it looks something like that. And if we're trying to consider the area between here and here, then we might make a choice to discretize here. So let's say I take these regions and I evenly mark them out. I don't have to evenly mark them out, but for convenience, I will. And let's say each of these is 1. You know, each of these has a width of 1. Then what I can do here is I can sort of easily get the area of one of these boxes, although if you notice, I'm going to overshoot the curve here a little bit. And I'm going to undershoot the curve on this next box. And then I'm going to undershoot again, right? But at the end of the day, I can get the area of each of these boxes, and I can sum up each of those areas, right? So that approach is called Riemann sum, and we're actually going to commit some code for that, applying to the normal distribution when we get to it. But I want you to kind of internalize this idea that we can construct in an iterative way, whether we do it by pen and paper or we do it by in some procedural way, we can construct a good approximation of the area of this region by sort of breaking it down into little rectangles and getting the area of each of those rectangles. And we're going to lose something along the edges. I'll just drive that point home. Oops. So we'll lose something along the edges when we do this. Maybe I'll just do a different plot here just to give this idea. So if I make these boxes, well, let's do this. I'll start a box here, right? And then my next box will go here. And my next box here. so on. One thing you might notice is that we actually do make up some area, right? So the area that we've lost over here, we are, we might be picking up some over here. And, there's different ways we can do this. This is a left Riemann sum. We could build our boxes, so that they overlap on the left side instead of the right side, or we can make them central, where on the curve, this is the point that hits the curve as opposed to this corner over here. There's different ways to do this, but kind of the takeaway is that this isn't the worst way to approximate the area under the curve. And if you're thinking about it, well, you can always divide these in half and do better, right? So we can always build some better precision. If I can draw straight, right? If we divide these in half, we're going to get closer and closer to the actual area if we do that. Right, and this one's already pretty good. And then, and so on. Like, I'm not going to fill the whole thing in, but if we continue to divide these in half, we are approaching the actual area. The better our approximation is going to be. Okay. So we talk about three continuous distributions in this course. We talk about a uniform continuous distribution, which we've already seen a discrete uniform distribution, right? We've seen that with rolling a die. 1 or 2 or 3 or 4 or 5 or 6, each of those have equal probability of occurring. And for a uniform continuous distribution, it's not that different, except remember, we've got this idea of infinite precision. So usually with continuous distributions, we're asking less than or equal to some value, or less than. And if you think about if it's infinite precision, less than or equal are the same thing. Or we're asking for the probability of something within a certain range. And we'll talk about that a little bit more. So we talk about a uniform distribution, which is just the continuous analog of a discrete uniform distribution. The exponential distribution, which models the time between Poisson events, right? Because Poisson models the number of events in a given span of time, independent events. But we can kind of pivot that and consider the amount of time, or the amount of area, or the amount of space between two different events. And then a normal distribution. This is the bell-shaped curve. So many things follow a normal distribution, and like I said, we kind of could allocate almost a whole course to studying the normal distribution in terms of stats. But in the DSI, you're going to apply a lot of things related to the normal distribution, but in this pre-DSI space, you don't need to know that much about it. We're mostly asking you about discrete distributions when it gets down to it. Okay, so let's just think about a uniform continuous distribution between 0 and 1. So if I'm drawing this, if you see something that looks like this, right? And this is 0, this is 1, or whatever this is. It could be n, 270. It could be anything. This is a uniform distribution, right? And kind of what we're seeing is that there is equal. If we take some range of values here, there's equal probability of any given value. And so why don't I do, say this is 0.5 to 0.6. What is the probability in a continuous uniform distribution of pulling a value between 0.5 and 0.6? So maybe a way to think about this is in a discrete way, right? If we break this down into, its discretized forms, then we're really just looking at 1 over 10 or 0.1, right? So let's think about another instance of this. Let's think about what is the probability. Let's say this is 0.68. What's the probability of getting a value less than 0.68? Yeah, what do you think about that? The probability of getting a value less than 0.68 from this uniform continuous distribution. So here's the thing, and I'll reiterate this. It'll come up again. This statement, 0.68. So if I say less than 0.68, this is actually the same thing as less than less than or equal to 0.68. Because again, we have infinite precision, right? So if we're talking less than a specific value, it's going to be, less than or equal to are going to mean the same thing. So I could say less than or equal to, and that'll be equivalent. So it's just 0.68. And, this, if we think about this a little bit further, in terms of maybe some other uniform distribution, where this is 255, and that's 0 still. We can still ask the same kind of question. Let's say we're dealing with, I don't know, what is the probability of getting a value greater than 235? And remember, greater than and greater than or equal to are the same thing for our purposes here. So what is the probability of greater than 235? Oh, shoot. There we go. Okay. Exactly, yeah. Yeah, it's 20 over 255. And I'm not sure what that is offhand, but somebody probably threw that into a calculator. Maybe that's 0.07. I'm not sure, but yeah, it's just 20 over 255, right? So this is pretty easy, right? These are pretty straightforward. I'm going to maybe make this a little more complicated, but hopefully not in a way that is, well, I'm going to do this in a way that is, kind of procedural. I'm going to tie it back into code. Some things about the uniform distribution. Expectation is just 1/2. It's just it's like a standard average, right? So the average, the mean from that distribution I just showed between 0 and 255 is just 255 over 2, right? So that would be our expectation. The variance is a little wild, and there's some theory behind this that I'm not going to get into, but I should make a video on that sometime and share it. Yeah, like the question why is the variance of a uniform distribution 1 over 12 multiplied by the difference between the high bound and low bound squared. Yeah, it's pretty cool. It's a little weirder than you might expect. Okay, so we're going to go through just this construction of a uniform continuous distribution. And oh, what did I just do? Oh, I see. Okay. And I'll do this in the uniform.py, which is in the folder that I slacked on GitHub, or the folder on GitHub that I slacked. Okay. So we'll just kind of figure this out. The first thing we're going to do is create a Bernoulli trial. Okay, so that's pretty easy. I'll just say from random import choice, and I'll define get bit, and this is just going to return a value from 0 or 1, right? So from here, we can just generate some random binary. Let's see. Call this generate binary, and we'll pass in n. Oh, 9. 9 is a weird number. We'll just do 8. Okay, so I'm just going to return, 8 bits randomly generated. I'm going to do that with a comprehension here. So return get bit for bit in range n. So let me test that in a second. Okay. Does everybody feel comfortable with this comprehension? I can break it out into a for loop if that's helpful. If you want me to do that, just put that in the Slack. But I'm going to assume you know what this is doing. It's just going to call get bit 8 or n times, right, and return a list of binary. Okay, so from here, I can get a float through the application of a geometric decay on this binomial process, right? This is a binomial process. It's a random binomial process. If I want to convert a length of binary into a float between 0 and 1, I can perform geometric decay with a probability of 0.5. Or it won't be a probability there. It'll be a decay factor of 0.5. So I'll call this get float, and I'll set n to 8, not 9. And I'll just get a list of binary, get binary of, sorry, this is generate binary. Okay. And what I can do with this is I'll set an accumulator. So I'll call this floats accumulator. And you don't have to set it at 0.0. I just like to do that because it communicates to whoever's reading the code that it's supposed to be a float. And then I'm going to apply a very kind of simple formula to this. It's going to be, if I have a binary list, 0, 1, 1, 0, 1, 0, let's say, I can sum the values in this list. Let's call this, this has a length n. So I can set I from 1 to n. And I'm going to take each of these bits, right? And I'll just call it, bit. I'll call it b, and I'll do b sub I. Let's think about this mathematically, where this is actually 1 indexed. Here are the indices, 1, 2, 3, 4, 5, 6. So let's just realize that that's 1 indexed, not 0 indexed. And I'm going to say b sub I multiplied by 1/2 raised to the index, raised to the I. So if we think about this, the b sub I is like a switch. It's like a on-off switch. Okay, it's either where 0 is off and 1 is on. And if this bit is 1, if this switch is on, right, then 1/2 to the I is going to be 1/2 to the first, or 1/2 to the second, 1/2 to the third, 1/2 to the fourth. We're applying a weight to each bit, right? So the weight of this first one is 0.5. The weight of the second one is 0.25. Weight of the third one is 0.125, and so on. So when we're looking at this, this binary right here, we would have a value that would be at least 0.375, right? It would be at least 0.375, and then we're getting smaller and smaller as we go to the right. Okay, so that's what I'm going to code here. So it's just index and bit and I'm going to enumerate because I want the indices. I'm going to enumerate the bin list, and I'm going to start at 1, as I did in the formulation for this. So the float accumulator, is that what it's called? Float accum is going to be incremented by the bit multiplied by 0.5 to the index. And then we can just return the float accumulator and the binary list. So if I print the result of this, the result of get float, I'm going to see something. Okay, let's see. So notice what I'm getting here. I'm getting this value, this float value, and maybe I'll just copy this. I'm getting some float value between 0 and 1. If I run this a bunch of times, and sort of push this into a dictionary and check to see what the frequency of certain values is, maybe I would dump these into buckets or something like that. If I do that, I'm going to see that this is generating a pseudo-continuous. It can't truly be continuous, right, because it's a computer, but it's generating a continuous value between 0 and 1. So this is a discrete process, right? There's a Bernoulli trial that we turn into a binomial process, upon which we apply some kind of geometric decay right here, and we get a continuous outcome. And that's kind of cool, right? So there is a very close relationship potentially close relationship between discrete and continuous distributions. We're going to see that with the exponential distribution, right? There's the exponential distribution is going to model time between Poisson events. There's a reason for that. Now, this isn't to say that every uniform distribution, continuous uniform distribution, is rooted in a discrete uniform distribution. That's just not true. It's just this is a process where we go from a discrete construction and we have this continuous manifestation, and it becomes higher and higher precision, right? This float will become higher and higher precision as we increase the value of n, right? As n tends toward infinity, which we can't really do on a computer, but if we could do that, then we are approaching a true continuous distribution. Okay. I think that's all I want to say about that. Yeah, I think so. All right, so let me pull the notes back up here. Okay, so we were talking about, that's pretty good for a uniform distribution. The main takeaway is if you are trying to figure out the probability of a certain outcome, right? And I'll just reiterate this visually. If you're trying to figure out the probability of, say, some outcome between this and this, right? And let's say this is A, this is B, and this is, I don't know, x1 and x2, then we can get the distance between x1 and x2, right? So the area here, the probability of this area, it can be expressed as x2 minus x1 over b minus a, right? That's how we can discern the probability of a certain range of outcomes in a continuous uniform distribution. Okay. All right. So the main thing that I'm going to ask you to remember about the exponential distribution is that it models time between Poisson events. So what do I mean by that? Let's say let's use time. I think time is easy to think about. If we have, I don't know, 5 minutes. If we have 5 minutes, and we have in 5 minutes we expect to see, 4 events, right? So that's a lambda of 4 in 5 minutes. Then we can start thinking about the way that those 4 events are spread across the 5 minutes. Roughly how much time would we be waiting? How much time would we expect to wait? And if we're thinking about this in terms of an expectation, well, whatever, if I evenly place these events, that's going to give us a sense of how much time we would expect to wait, right? It's sort of boneheaded even. It's like, oh, well, if we just evenly spread these events out in 5 minutes, well, that would reflect the expectation of the amount of time we would need to wait. It turns out that is the case. It also turns out that the probability of waiting a certain amount of time is going to follow an exponential distribution. And this is going to, if you're thinking about the Poisson PMF, you can kind of see very clearly the relationship between the Exponential Pdf and the Poisson PMF. So we're going to have a breakout. I'm going to have you code up these 5 exponential functions. And yeah, we'll do 5 minutes on that. I think that makes sense. So you're going to code the Exponential Pdf, which is represented here. If we know lambda, then then the exponential Pdf is going to be lambda multiplied by e, Euler's number, right, raised to the negative lambda times x, unless the value is the value for which we're looking for the probability is less than 0. And then we've got this expectation. Notice that the expectation here is just 1 over lambda. That kind of makes sense, right? And then there's a CDF here. This is a really convenient closed form CDF. It's the exponential CDF is really friendly for being a continuous distribution. A lot of continuous distributions we don't necessarily have. For uniform it's really friendly too, but for a lot of continuous distributions we don't have a simple way to represent less than or equal to some number, right? And then the variance is also really straightforward, just 1 over lambda squared. Okay, so I'm going to put 5 minutes on the timer, and then we'll code these out, and there will be a breakout that utilizes these. Okay.
Time's up.
If you're still working on it, I can give a couple more minutes. Give me a thumbs up if you want that. Okay, I'm gonna go ahead and start coding through some solutions. I'm gonna just grab all of these and just take a second. I'll move all of these over here. Okay. So I'm putting this in the exponential.py file. And the first thing we'll code, well, we need to import some things. I'm going to import two things. I'm going to import E, right? That's definitely we'll need that. And then I'm actually going to import a square root function. Oh, one sec. My dog is kind of freaking out. Just 10 seconds here. One sec. Cool. Sorry about that. Okay. So call this Exponential Pdf, and we're going to pass in lambda and x, right? That's what we're seeing here. And this is just lambda times e to the negative lambda times x. So we can return lambda multiplied by e raised to the negative lambda multiplied by x. But the thing is, there's also a condition here, right? This is for x is greater than or equal to 0. Since we don't have a concept of negative time that we're working with, I'm just going to also put this in here. So if x is less than 0, we'll return 0. Okay. So we would expect that to work. I'll do the Exponential Cdf next. And this is, very similar. I'm actually just going to copy all of this and change this to Cdf. And this is the same. If x is less than 0, return 0. And instead of lambda multiplied by this, I'm going to say 1 minus e to the negative lambda times x. So just a small modification there. And now let's do the mean. So just def exponential mean lambda, and then we can just return 1 over lambda. And then we've got the exponential variance, and again, we just pass in lambda on this. And this is returning 1 over lambda squared. And then finally, the standard deviation, right? And that's why I imported that square root. So this is just, well, I'll copy this, change that to std, and then instead of performing that calculation again, I'm just going to do that, and I'm going to wrap that in the square root function. So that's, yeah, it's just that. I'll paste this into, oh, whoops. Oh no, I'm one space off on everything. It's awful. Okay, all right. Now I'll put this in the Slack for anybody who will need it on the next problem. Okay. Yeah, and with these, I think it's really helpful to just, just kind of tool around on the internet and find things that find mathematical functions that you can implement in code, and then play around with them. Right? That's something that we've been doing. But my go-to, one of my favorite things to watch on the internet is Numberphile. I don't know if any of you all watch Numberphile. Um, they just have really great, accessible, and interesting math videos. And I'll go and I'll watch one of their videos and I'll just make code for the thing that they're talking about. It's yeah, just something like entertaining for myself, because I often don't just want to watch something. I want to like feel engaged with it. And with that material, they'll present these really cool concepts, and they'll be drawing it all out on construction paper. And when I watch it, I'm thinking, oh well, how would I write code for this, or at least write code that can make estimations in that regard. So if you're ever looking for stuff like that, I think Numberphile is a really, really good one. Okay, so we're going to do another breakout, and I'm going to put 4 minutes on this, because I think some of you will be copying and pasting that code, and you'll need all of that. So suppose you're on a street corner trying to hail a taxi cab. You're going to let x be the amount of time in minutes that you have to wait, or we're going to consider the random variable x as representing the amount of time in minutes that you have to wait. And x follows an exponential distribution with a lambda of 0.1. And what we mean by that lambda, I'm not sure why we have this lambda hashed here, but what we mean by the lambda is the rate of cab arrivals is 0.1 cab per minute, right? So think about that in terms of the the amount of time we have. So what's the probability that you'll have to wait more than 10 minutes? What is the amount of time that you would expect to wait? And what is the variance or standard deviation of this random variable? So I'll put 4 minutes on here. And this is just you applying those formulas. Okay, let's look at how to think about this, how to answer it. So I'm going to copy all of this over. All right, so suppose you're on a street corner trying to hail a taxi cab. Our lambda is 0.1. So why don't I just put that first, 0.1, and we're just going to apply these directly. So what's the probability that you'll have to wait for more than 10 minutes? Okay. Well, whenever we're asking a question less than or greater than, usually we're going to think about that in terms of a CDF, right? So, okay, let's answer that. So let's think about this. It's going to be the exponential CDF, where we pass in lambda, right? And if we're thinking about more than 10 minutes, then really we're thinking about the complement of less than 10 minutes. So I'm going to set x to 10, and I'm going to do 1 minus all of that. So let's look at what that is. Print exponential, Python exponential. Okay, so it looks like that's 0.367 or 0.368 roughly. So let me just put that in. All right. What is the amount of time that you would expect to wait? Now, if you think about this, this just sort of can pop out, right? Like, how much time would you expect to wait if, it's 0.1 cabs per minute, right? I think that, well, we can answer this with the exponential mean function, but if we think about it just logically, we can see that it's 10 minutes, right? Okay. So what is the variance of the random variable? Let's put in the exponential variance, and I'm also going to print out the exponential standard deviation. Okay, so notice our variance is really out of scale, and I think standard deviation serves us a little bit better here, right? So we're going to expect to wait 10 minutes with reasonably 10 minutes on either side of that. Okay, so let's take a break. Let's take a 6-minute break, and I'll see y'all back here, and we'll get started on things related to the normal distribution. Okay, see y'all in a little bit. All right, so let's start thinking about the normal distribution. So this is our classic bell-shaped curve. When we see it, we often will describe distributions that are not normal distributions as being normal-like, or as having bell-shaped curves. In fact, binomial distribution with a probability per trial of 0.5 will have a normal-ish behavior, and we can even use it at times to model a normal distribution, but that's kind of a different topic. But yeah, so we've got something that looks like this, right? And we're centered around the mean, and we have, of course, we have standard deviations out from the mean. And we think about this when we define a normal distribution. We assume that the variable is distributed normally, right? We assume that with a mean of mu and a standard deviation of sigma. So this is the shape. We could spend a whole course on this, and I think in the next round of this, I'm probably going to devote a whole class to it instead of the half class that we do, just because I think it does deserve it. We're not going to go as deep into this as we probably should, but there's also a universe of materials out there, and I'm probably going to make some supplemental videos on the uniform distribution, on the normal distribution really soon, just to fill in some gaps. But yeah, there are tons of phenomena like that follow normal distributions, like the heights of people. That follows a normal distribution. If you considered a bimodal distribution based on biological sex, for instance, then we've got biological males, biological females, and we actually have a bimodal distribution that is composed of, right? We have some sort of composition with two modes, right? Where those two modes are the mu's, are the means of each individual distribution. But there are a lot of things that are either composed of normal distributions or just follow a normal distribution, like heights of trees in the forest. For some interval of tree age, that's going to follow a normal distribution. That's really, really common. So, yeah, and this comes up kind of a lot, right? The central limit theorem, confidence intervals are composed using the normal distribution. Statistical inference hinges on the normal distribution, and it applies in a bunch of other places. So here is the normal PDF, and I'll make this a little bit bigger. You're going to implement this in code with the parameters that are defined up here. Let's do 4 minutes on that, and make sure to test this because yeah. So here's just a little test snippet. If you put in 0.5 for mu, 0.5 for the value of x, 0 for mu, and 1 for sigma, you should get a value of 0.3521. So I'll set a timer for 4 minutes and go ahead and code that up. Okay, did anybody get there? Okay. Let's see. Let's give 2 more minutes on this. Just want to see a few more solutions come in. Okay, so let's go through a solution of this. And I want to be clear what we're seeing when we pass in values to the normal PDF. This isn't getting us out a probability per se, right? This is getting us a value that we can use in the cumulative density function. So if we're saying this is 0 and we have a standard deviation at 1 and we're looking for the value at 0.5, what we're getting is the height here. So this is essentially f of x, and these are our x values, and these are our y values. So we're getting the value out here. So we're going to use that in the cumulative density function. Okay, so I'll go ahead and code through this. I'm going to need a couple things here, right? I'm going to need E. So from math, import E. And it looks like there's pi in here, right? So I'll get pi out of this. And there's a square root, and I like to use the square root function to do this. So I'm just going to import square root from math. It's slightly faster. I don't know. It's not really a big deal. So let's do normal PDF. We'll set an x at 0, mu at 0, and sigma at 1. So this mu and sigma, it turns out that if you have a mu of 0 and a sigma of 1, you've got a normal distribution in standard form. And we're going to see what standard form, reasonably what that means. It's actually a convenience form of the normal distribution. So let's break this out into parts. I think it's helpful to do that. Oops. we'll just do this part first. So that's going to be 1 over our value of sigma, right? And wrap all sigma multiplied by the square root of 2 times pi. Okay, so I'm going to contain that also in parentheses. I don't need to, but I'm going to just so that we kind of isolate all of this, okay? And then this next part, well, that's just multiplied by e, right? E raised to a bunch of stuff. So we've got negative 1 over 2, right? Negative 1/2 multiplied by, put this in parens as well, x minus mu divided by sigma, and then that is squared. Okay. This function is really easy to make mistakes, to have typos in. So there's a good chance that there is a typo in here, and that's why I put that little test snippet in there, just so that we could make sure. So you'd have something to make sure that it's doing what you expect it to do. Oh. Okay. Okay, so that looks correct. 0.352, etc. Yeah, totally. I've been teaching this, and I miss a parentheses, and it keeps giving me a wrong number, and I can't see where it actually is. Yeah, it's nice if you can just break it out as far as possible, so that you can eliminate that potential. But it is really easy when you're implementing functions that have this kind of like, rational functions with this level of complexity. It's hard to get that code written well on the first try. Okay, so there's that. All right, so when we're looking at the normal distribution, usually what we're trying to get out of it is, do we care what this height is, right? Let me answer this question. Yeah, I think it is better to write the code in chunks. Definitely. Yeah, if you can chunk it out, right? If you can just, think of it as modular with components. Yeah, first part, second part, and then multiply those two parts together. I think that if you can determine your kind of how you fix for your expected value, right? That's through your tests. If you can figure that out, then you can often diagnose what's going on there. But yeah, it's hard with some of these complex functions. Sometimes you just have to grind through it and try to write it a few times. And if you know what it's supposed to return, then you do that until you get the right results. I don't know of a much better way to do that unless you're really breaking out the function into atomic functions, into the smaller component functions. But you should really only do that unless those, if those are useful, right? Okay, so right, this was our value 0.5. Most of the time, we're not trying to figure out what this is up here, right? That's not really that useful to us. Well, here's the thing. It's going to be useful to us in a second. But usually we're trying to figure out the area under this curve. And this is kind of bringing it back to what I was talking about earlier. So this is what a CDF does for us. And often it's like, often we have some sort of usable CDF, whether it's, an accumulator pattern over some, with discrete distributions, probability mass functions, we can accumulate over a probability mass function. That's fine. And with the exponential distribution and with the uniform distributions, our CDFs were relatively simple, right? They were just either closed form or kind of implicit in the distribution itself. In this case, we've got this function is complex in a way that we don't really have a closed form that will tell us this area. And so there are different ways to integrate this. Let me retract that. There aren't any great ways to integrate this except through using Riemann sums. And I'm going to present you something that's pretty challenging, and it's very okay if you can't figure out how to do it. Okay, that's really okay. I'm going to give you some starter code on it, but I'm going to try to explain to you what it'll be doing. So, we're not quite there yet. We're going to kind of finish on that note. First, we're going to use the classic approach for applying the CDF. And that's, unfortunately, or maybe, I don't know, it's using tables, right? Where we look this up in a table. We get some value that we then look up in a table to get the probability of getting less than or equal to a certain amount. That's, how people have done this for ages. And, the modern way to do it is to use some programming package, like SciPy stats. That's mostly what you're going to be doing in the future. But I want to show you how to do this by hand right now. And I also want to show you how to potentially code the CDF using an accumulator pattern, even though it's going to be a little cryptic and, a little bit above the level of skill that we're expecting. So there's this table, okay? This thing called a z-score table or a z-normal table. And so given a z-score, and we'll talk about what that is in a second, the z-score represents the number of standard deviations a value is away from the mean, okay? You reference this normal table to find a given probability. So we're usually thinking about the probability that big X is less than or equal to some little x, right? But here we're thinking in terms of something that we're calling z. And we can calculate the z-score. So the way that we do this is we subtract the mean and divide by the standard deviation. And that's going to give us kind of this normalized value that will fit in a distribution that has a mean of 0 and a standard deviation of 1. And that it's not, I'm just going to say you're probably not going to do this in the future, but I just want to show you one time how to do this. And we'll do that with just a simple example. So scores on the verbal scholastic aptitude test follow a normal distribution with a mean of 475 and a standard deviation of 98. So we've got mu. Let me pick a better color. So we've got a mu of 475 and a standard deviation of 98. Okay. So the first thing we're going to do is find the z-score. And all we do here is we subtract from the value we're looking for, we subtract mu. So we're trying to get the probability that x is less than 300. Okay? So if I draw this out a little bit, we've got a mean of 475. We've got a standard deviation of 98. So this is 475 minus 98, 475 plus 98. And you can see that we're looking for the probability of something down here, right? So we're already reasonably thinking this is fairly improbable, right? If we just draw this out. So in this process, I'll just set this over here for a sec. When we're thinking about how to determine this relative to a standard normal distribution, then we can standardize against mu and sigma, which we're doing here. So we're just going to take 300, which is our value of this big X right here, right? So 300 minus 475 over 98. And if we process that, this is going to be z. Z being less than this, we get a value of negative 1.79. So our z-score is going to be negative 1.79. So if we think about this in terms of, oh my gosh, my cat. Okay. All right. If we think about this in terms of a standardized normal distribution, then I think there's a way that maybe this can click into place a little bit better. So we've got this standard normal distribution centered at 0 with a mu of 0, right? Standard deviations are, right, here's our negative 1, and we're looking at something somewhere down here at negative 1.79. And we're looking at everything from negative 1.79 down to negative infinity, right? So this is an analogous distribution. And because we've normalized it and it's analogous to what we see up here, we can simply find the probability that in this standardized normal distribution that we get a value less than negative 1.79. So that's what these tables are constructed of, right? That's what this z-score represents. So if we want to do that, then we can jump up to this table, and maybe I'll screen capture this and kind of blow it up a little bit. And the process for so this is actually the process. This is the process I did in stats classes. You find negative 1.7, and then you take it to a further precision, which is going to be 0.09. So negative 1.7, minus 0.09. We can follow this all the way over, and this all the way down. And the probability is going to be 0.0367. So how do we interpret that? That probability is the actual probability that we're looking for. We've just obtained it through an analogous distribution, not through the actual distribution. So this symbol here, this phi, all this means for our purposes here is there's some function that represents that table. So we're looking up the z-score, negative 1.79, and the result is going to be 0.0367. And the way that we interpret that is that there is a 3.67% chance, or a 0.0367 probability, that a randomly chosen SAT verbal score will be less than or equal to 300. So that's terrible, right? That's all like pretty awful. You could spend all day doing this sort of problem. It's honestly not that bad, but that's not what we're generally going to do. We're going to call out to a stats library in general. We're going to call out to SciPy or stats models or some other library that we're familiar with. So that's not necessarily what we're going to do right now. What we're going to do right now is code something up that will get us this that'll get us this value, and we're going to do this through building Riemann sums. It's going to be a little bit, it's going to be a little weird. I'll just say that. But let me just give you this idea of Riemann sums one more time. And right, we've got some normal distribution. And what we can do is break our x values into little chunks, right? We can break these into little chunks. And we're going to make an arbitrary negative infinity. We're just going to make some kind of lower bound here. It's obviously not going to be negative infinity, but we'll start with some very small value. And what we'll do is we'll build rectangles, right? We're just going to build rectangles. And if you think about it, well, we've got the PDF, right? The PDF is going to get us this value, the edge of our rectangle. And so we can build rectangles and just sum, here's, I don't know, x1 plus x2 plus x3 plus x4. We can just sum all of these. So really what we need are these, we need these increments. We need to determine those increments. I'm going to provide you with that because I think that's kind of the weirdest, trickiest part. And I'll provide you with a modifier on the return as well. And I'll leave you to write the code in the middle where you sum up the areas of each of these rectangles up to whatever the x value is that you're looking for, whatever that might be. So let me give you some code to work with. So I'm going to call this normal CDF. And I'll just give this some, just basic values. So x of 0, mu of 0, and a sigma of 1. So by default, standard distribution. I'm going to give you this, the vowels. So these are your x vowels. Maybe I'll just call it that. And it's going to be num for num in range negative 1,000. So I'm going to go from negative 1,000. We're going to assume we're not, escaping. We're not going to have a mu of negative 5,000 or something. We're just going to assume we're going from negative 1,000 up to x times 1,000. And I need to cast this to be an integer. And we want to be fairly granular with this. So I'm actually going to modify all of these numbers by 0.001. Okay. So this is going to get us a range of values, and then you're going to pass these into your PDF and accumulate the areas of those rectangles. And I'll put this snippet in the Slack in just a second. When this is all said and done, you're going to return whatever your accumulator is multiplied by 0.001. So that's just going to kind of correct it. Because if you sum it like this, this is just a correction on the result. So let me put that in Slack. And let's do 7 minutes on this. Yeah, so that's the task that's in front of you. I know it's tricky. It's okay if you don't get it working the way you expect, but it is actually a fairly simple accumulator problem once you figure it out. So I'll put 6 minutes on the clock actually. Okay, I'm going to show you a simple way to do this. And I'm going to ask what might go wrong with this. So yeah, let's it's actually fairly simple. So I'm just going to make an area accumulator. Start that at 0. And then I can say for each value in xvals, the result is just going to be the normal PDF, right? The normal PDF of val, mu, and sigma. And I can take the result of each of these calls, right? This is the area of just one of those Riemann boxes, right? One of those Riemann rectangles. So I could accumulate against that result. I could say accum plus gets the result, but I can just do this. I'll just go ahead and make that one line instead. And then what I'm going to do here, if the value is greater than x, I'm going to break. And this is not something that's obvious. It's to cover an edge case that can occur, but in general, this should be fine. Int x times 1,000, and then turn into a float. This should be okay, even without this break. So if you didn't include that, that's totally fine. Okay, so let's put in the values that we saw for that SAT problem. So this is just what x was 300, right? Score of less than 300, and then mu was 475, and sigma was 98. So what did we see before? Let me look that up really fast. The probability we saw from the table was 0.0367. So what do we get here? We get 0.371 approximately. So there is a difference there, and there's a reason for this difference. The scheme that we have right here, this works reasonably well. If we became more precise, would that help? Probably not. Well, no, sorry, it would. We'd have to increase our range. We'd have to generate more x values and everything. The other thing we could do is we could just get a z-score, right? We could write a z-score function, and that would actually then we could call the normal CDF on these values, process those values into a z-score, and using this same scheme, we'd get more precise outcomes. Using this x interval approach, right? We're not going to worry about doing that right now. This is just to show that you can take a function and get the area under the curve for a specific range using some kind of accumulator approach, right? So even if you have a very complex function, something that, I don't know, you don't really have a sense of how you're going to put that together, you can simply call the function in a Riemann Sums approach and get a result. So this is more to demonstrate that. In the wild, what you're going to do is use SciPy stats and use the CDF on a normal random variable. Okay, so I think we've got one breakout here, and I'll paste this code in really quick in case you need to use it. Yeah, and this is a short breakout. A radar unit is used to measure speeds of cars on a motorway. The speeds are normally distributed with a mean of 90 kilometers per hour and a standard deviation of 10 kilometers per hour. What is the probability that a car picked at random is traveling at more than 100 kilometers per hour? So I'll put 3 minutes on the clock and see if you can solve that. All right, let's solve that. Pull the problem up. So a radar unit is used to measure speeds of cars on a motorway. A mean of 90. Okay, so, you know what? I should just copy all this text. Okay, so we've got a mean of 90, standard deviation of 10, so sigma of 10. The probability that a car picked at random is traveling at more than 100 kilometers per hour. So more than is the complement of the CDF, right? So we can call, well, we'll set our x at 100, and we'll call the normal CDF, right? That's what we called it, yep. And let me get the actual. So we'll pass in x, mu, and sigma. And we're taking the complement of that. I'm getting 0.15, roughly 0.157. And the way that we would interpret that is that there is a 15.8% chance that a random car picked is traveling more than 100 kilometers an hour. Okay, so we're gonna stop there. That's it's cool. I think I timed this pretty well, actually. In our next class, we're going to be doing pen and paper, and it's all going to be conditional probability. I'm going to try to have those slides done by somewhere in the middle of the day if you want to preview them for a bit. Also, we don't test you on conditional probability. Let me be careful about saying this. We don't test you on Bayes' theorem in the technical interview, but Bayes' theorem is going to be very important in the DSI, and we cover it pretty extensively in the pre-course. We take a few different approaches with it. It's a good thing to get some practice in, and it kind of when you get into conditional probability, I think a lot of other probability starts clicking, right? Like when we're asking something in light of something else, it really makes probability, I think, make a little more sense. That's class for today. Feel free to stay on if you have any questions. Otherwise, I will see y'all tomorrow. Yeah, and thanks everybody. Have a great night. Feel free to sign off.